The universe is a boundless expanse filled with wonders that challenge everything we think we know. Among the stars and galaxies, there are celestial objects so bizarre, so utterly mysterious, that they seem to defy the very laws of physics. These cosmic enigmas have puzzled scientists for decades, sparking debates, fueling theories, and igniting our collective imagination. From black holes that warp the fabric of space-time to ghostly remnants of ancient stars, the cosmos holds secrets that are as fascinating as they are elusive. But what if I told you that some of these objects are so strange, they're almost impossible to explain? Today, we're diving into the most mysterious celestial objects floating in the vastness of space phenomena that stretch the limits of our understanding and leave us questioning what else might be out there. We'll explore bizarre anomalies, unexplained glimmers of light, and the cutting-edge science attempting to unravel these cosmic riddles. So, as we gaze into the infinite void, one question lingers: what could be out there waiting to be discovered? Picture this: 85% of the universe is made up of something we can't see, touch, or even directly detect. This invisible giant is dark matter, a mysterious substance that holds galaxies together, bends light, and shapes the very structure of the cosmos. Yet, despite its overwhelming presence, dark matter remains one of the greatest unsolved puzzles in modern science. How can something so pervasive be so elusive? The evidence for dark matter lies in its gravitational fingerprints. Galaxies spin faster than they should, given the amount of visible matter they contain. Light from distant stars bends in ways that suggest something massive is warping space-time. These cosmic clues point to the existence of an invisible force, one that doesn't interact with light or ordinary matter, but exerts a powerful gravitational pull. It's as if the universe is playing a game of hide and seek, and we're still searching for the rules. Scientists have proposed a range of theories to explain dark matter. One leading idea involves WIMP, or weakly interacting massive particles. These hypothetical particles could be floating through space, passing through us unnoticed, interacting only through gravity. Another contender is the action, an ultra-light particle that could be hiding in the quantum realm. Yet, despite decades of experiments, from deep underground detectors to space-based observatories, dark matter continues to evade detection. The search for dark matter isn't just a scientific endeavor. It's a quest to understand the very foundation of the universe. If we could uncover its secrets, we might finally grasp why galaxies behave the way they do, how the universe evolved, and even what lies beyond our current understanding of physics. But for now, dark matter remains a cosmic enigma, a shadowy presence that challenges our most brilliant minds. Could this invisible force hold the key to unlocking the universe's deepest mysteries? As we ponder this question, another astonishing phenomenon awaits our exploration, one that shines brightly yet defies all expectations. Black holes are the universe's ultimate enigmas, cosmic vacuum cleaners with a gravitational pull so intense that not even light can escape their grasp. Imagine a region of space where the rules of physics as we know them cease to apply, where time slows to a crawl, and matter is compressed into an infinitely dense point known as a singularity. This is the heart of a black hole, a place where our understanding of reality breaks down completely. It's as if the universe has drawn a curtain over these objects, leaving us to wonder what truly lies within. The concept of a singularity is both fascinating and unsettling. At the center of a black hole, matter is crushed to a point of infinite density, creating a gravitational well so deep that it warps the fabric of space-time itself. Here, the equations of general relativity that govern gravity reach their limits, and our current theories simply can't explain what happens next. It's a cosmic riddle that has challenged physicists for decades, sparking debates about the nature of reality and the limits of human knowledge. Adding to the mystery is the paradox of information loss. According to quantum mechanics, information about the state of matter can never be truly destroyed. Yet, when matter falls into a black hole, it seemingly vanishes from the universe, taking its information with it. This contradiction has led to one of the most profound puzzles in modern physics. Is information truly lost, or is it somehow preserved in a way we don't yet understand? The answer could reshape our understanding of the cosmos. Recent breakthroughs have brought us closer to unraveling these mysteries. In 2019, humanity captured the first ever image of a black hole, a monumental achievement that showcased the shadowy silhouette of an event horizon, the point of no return. This groundbreaking image not only confirmed the existence of black holes, but also opened new avenues for studying their behavior. Meanwhile, the concept of Hawking radiation, proposed by physicist Stephen Hawking, suggests that black holes aren't entirely black. Over unimaginable timescales, they can emit faint radiation, slowly losing mass and energy. This discovery hints that black holes might not be eternal, eventually evaporating into nothingness. But for all we've learned, black holes remain shrouded in mystery. What lies beyond the event horizon? Is it a one-way journey into oblivion, or could there be something more, a gateway to another dimension, a hidden universe, or a place where the laws of physics are rewritten? As we continue to probe these cosmic giants, one thing is certain: black holes are not just anomalies in space, they are windows into the deepest questions about existence itself. And as we venture further into the unknown, another astonishing phenomenon beckons, one that challenges our understanding of time and space in ways we're only beginning to comprehend. Now, let's turn our gaze to one of the most extreme objects in the cosmos: neutron stars. Born from the explosive deaths of massive stars, these remnants are the densest objects in the universe, packing more mass than our Sun into a sphere no larger than a city. To put it into perspective, a single teaspoon of neutron star material would weigh billions of tons here on Earth. It's a staggering thought. Imagine holding a mountain range in the palm of your hand. But density is just the beginning of what makes neutron stars so utterly fascinating. These stellar relics spin at mind-boggling speeds, some rotating hundreds of times per second. Imagine a cosmic lighthouse, its beam of light sweeping across the universe in a blur. This rapid rotation, combined with their intense magnetic fields billions of times stronger than Earth's, creates an environment so extreme that it defies our everyday understanding of physics. Neutron stars are like natural laboratories, pushing the boundaries of what we know about matter, energy, and the forces that govern the universe. But perhaps the most tantalizing mystery surrounding neutron stars is their potential connection to fast radio bursts, or FRB. These are incredibly brief but immensely powerful blasts of radio waves that last just milliseconds yet release as much energy as the Sun does in days. FRBs have been detected from all corners of the cosmos, and while their origins remain uncertain, neutron stars are among the top suspects. Some scientists believe that FRBs could be produced by magnetars, a type of neutron star with even more intense magnetic fields. When these magnetic fields snap and twist, they might unleash bursts of energy that ripple across the universe. Yet, despite this compelling theory, the true nature of FRBs remains shrouded in mystery. What makes neutron stars even more intriguing is their potential role in unlocking one of the greatest puzzles in physics: quantum gravity. This is the elusive theory that seeks to bridge the gap between the world of the very small, governed by quantum mechanics, and the vast cosmos, ruled by general relativity. Neutron stars, with their extreme densities and gravitational fields, could provide the perfect testing ground for such a theory. Studying how matter behaves under these conditions might offer clues to how gravity operates at the quantum level, a question that has stumped physicists for decades. Could these tiny yet immensely powerful stars hold the key to understanding the fundamental forces of the universe? As we peer deeper into their mysteries, we're reminded that the cosmos is full of surprises, each one challenging our assumptions and expanding our horizons. And as we continue our journey through the universe's most enigmatic objects, another question arises, one that takes us to the very edges of space and time, where reality itself may bend in ways we're only beginning to imagine. Let's shift our focus to one of the most dazzling phenomena in the cosmos: quasars. These celestial powerhouses are the brightest objects in the universe, outshining entire galaxies with their staggering brilliance. Imagine a single object so luminous that it can be seen from billions of light years away, shining across the vast emptiness of space. But what exactly are quasars, and what makes them burn so fiercely? At the heart of every quasar lies a supermassive black hole, a cosmic giant millions or even billions of times more massive than our Sun. But unlike the black holes we've discussed earlier, quasars are far from dormant. As matter spirals into the black hole's gravitational grip, it forms an accretion disk, a swirling, superheated maelstrom of gas and dust. Friction within this disk heats the material to unimaginable temperatures, causing it to glow with the energy of trillions of suns. This incredible process transforms quasars into beacons of light that can outshine everything else in their vicinity. Quasars aren't just fascinating for their brightness, they also offer a window into the early universe. These cosmic lighthouses were far more common billions of years ago during a period known as the Cosmic Dawn. Back then, galaxies were young, and supermassive black holes had an abundance of gas and dust to feast on. This era of frenzied activity allowed quasars to dominate the cosmos, illuminating the darkness of the early universe and shaping the galaxies we see today. It's as if these brilliant objects were the architects of the cosmic landscape, carving out the structures that would define the universe for billions of years to come. Yet, as the universe aged, quasars began to fade. The once abundant fuel that powered their brilliance grew scarce, and the supermassive black holes at their centers became quieter, more subdued. This raises a compelling question. What caused these cosmic powerhouses to dim? Was it the exhaustion of their fuel supply, or did something else trigger their decline? The answer remains elusive, but studying quasars could provide clues about how galaxies evolve over time, and how the universe itself transitioned from its fiery youth to the relatively calm state we observe today. Quasars also challenge our understanding of energy and matter. The sheer amount of energy they emit defies conventional explanations, pushing the limits of what we thought was possible. Some quasars even produce jets of particles that travel at nearly the speed of light, stretching across millions of light years and impacting their surroundings in ways we're still trying to comprehend. These jets are like cosmic rivers of energy, carving paths through the fabric of space and influencing the formation of stars and galaxies. So, what fueled these cosmic powerhouses, and why did they fade into obscurity? The answers lie hidden in the distant reaches of the universe, waiting to be uncovered by the next generation of telescopes and observatories. As we continue to study quasars, we're not just exploring the past, we're also uncovering the processes that shape the cosmos as we know it. And as we turn our attention to the next mystery, we'll delve into another enigma that blurs the line between the known and the unknown, a phenomenon that challenges our understanding of space, time, and reality itself. Now, let's venture into one of the most profound mysteries of the cosmos: dark energy. While dark matter binds galaxies together, dark energy has the opposite effect. It's the mysterious force driving the universe to expand at an ever-increasing rate. This revelation has turned our understanding of the cosmos on its head, challenging everything we thought we knew about the fate of the universe. But what exactly is dark energy, and how did we come to discover its existence? The story begins in the late 1990s when astronomers made a startling discovery while studying distant supernova. These exploding stars, known as Type Ia supernova, serve as cosmic mile markers because they shine with a predictable brightness. By measuring how far away these supernovae appeared, scientists could determine how fast the universe was expanding. To their astonishment, they found that the expansion wasn't slowing down as expected but speeding up. It was as if some invisible force was pushing the universe apart, counteracting the pull of gravity. This force became known as dark energy, but dark energy wasn't just detected through supernova. The cosmic microwave background, the faint afterglow of the Big Bang, also provided crucial evidence. Tiny fluctuations in this ancient light revealed the universe's composition, showing that dark energy makes up about 68% of the total energy in the cosmos. Together with dark matter, these two invisible entities dominate the universe, leaving ordinary matter, everything we can see and touch, as a mere fraction of what exists. So, what could dark energy be? One leading theory is the cosmological constant, an idea first proposed by Albert Einstein. He introduced it as a mathematical fudge factor to keep the universe static, but later discarded it when Edwin Hubble discovered the universe was expanding. Ironically, the cosmological constant has made a comeback, now seen as a possible explanation for dark energy. It suggests that empty space itself has an intrinsic energy, constantly pushing the universe outward. Yet, this idea raises its own questions. Why does this energy have the value it does, and what causes it to exist at all? Another intriguing possibility is quintessence, a dynamic field that changes over time. Unlike the cosmological constant, quintessence could vary in strength, potentially explaining why the universe's expansion rate has changed over billions of years. But here's the catch: we have no direct evidence for quintessence, and it remains purely hypothetical. Both theories highlight the challenge of studying something that's invisible, intangible, and seemingly everywhere at once. The implications of dark energy are staggering. If the universe continues to expand at an accelerating rate, distant galaxies will eventually move so far away that their light will never reach us. Over trillions of years, the cosmos could become a vast, empty void with galaxies isolated and alone. This raises a haunting question: is dark energy tearing the universe apart? Could it one day lead to a big rip, where even atoms are pulled apart by the relentless expansion? For now, dark energy remains one of the greatest unsolved problems in physics. It challenges our understanding of gravity, space, and time, and forces us to rethink the very fabric of reality. As we probe deeper into this cosmic mystery, we're reminded that the universe is far stranger and more complex than we ever imagined. And as we turn our attention to the next enigma, we'll explore another phenomenon that blurs the line between the known and the unknown, a mystery that could reshape our understanding of existence itself. Among the countless wonders of the cosmos, there exists a peculiar class of celestial wanderers, rogue planets. Unlike the planets in our solar system, which orbit a star, these mysterious worlds drift alone through the cold, dark expanse of space. Picture a planet untethered from any sun, endlessly roaming the galaxy, shrouded in eternal night. It's a haunting image, isn't it? But how do these rogue planets come to be, and what secrets might they hold? Rogue planets likely form in one of two ways. Some may start their lives like any other planet, born from the swirling disks of gas and dust around young stars. But through violent gravitational interactions, perhaps a close encounter with another planet or a passing star, they're flung out of their systems, cast adrift into the void. Others might form directly from collapsing clouds of gas and dust, never tethered to a star in the first place. These solitary worlds are born in the darkness, destined to wander the galaxy alone. Detecting rogue planets is no easy feat. Without a star to illuminate them, they're incredibly faint, lurking in the shadows of space. Traditional methods of finding planets, like observing the dimming of a star's light as a planet passes in front of it, simply don't work here. Instead, astronomers rely on a phenomenon called gravitational microlensing. When a rogue planet passes in front of a distant star, its gravity bends and magnifies the star's light, creating a brief but detectable signal. These fleeting events are like cosmic breadcrumbs, hinting at the presence of these hidden worlds. Recent discoveries have revealed just how common rogue planets might be. In 2021, astronomers identified a free-floating planet roughly the size of Earth, drifting through the Milky Way. This groundbreaking find suggested that rogue planets could number in the billions, possibly even outnumbering stars in our galaxy. If that's the case, these lone worlds could be among the most abundant objects in the universe, silently traversing the cosmic expanse. But what makes rogue planets truly fascinating is the possibility of life. While they lack the warmth of a star, some could harbor subsurface oceans heated by internal radioactivity or tidal forces from a moon. Imagine a world where life thrives in the darkness, hidden beneath a frozen shell sustained by geothermal energy. It's a tantalizing thought, one that challenges our assumptions about where life can exist. Could rogue planets be the ultimate cosmic survivors, carrying the seeds of life across the galaxy? As we ponder these questions, another thought emerges. Could rogue planets be more common than we think? If so, what does that mean for our understanding of the universe and our place within it? These lone wanderers remind us that the cosmos is full of surprises, and that even in the coldest, darkest corners of space, there's still so much to discover. And as we turn our attention to the next mystery, we'll explore another phenomenon that pushes the boundaries of our imagination, one that challenges our understanding of time, space, and the very nature of reality. Deep within the cosmic tapestry lies a phenomenon so extreme, so utterly powerful, that it defies comprehension. Magnetars. These are not your ordinary neutron stars. Imagine a celestial object with a magnetic field so intense it could erase the data on every credit card on Earth from halfway across the galaxy. That's the sheer magnitude of a magnetar's power. With magnetic fields trillions of times stronger than Earth's, magnetars are among the most violent and mysterious objects in the universe. But what makes them so extraordinary, and why do they captivate scientists and stargazers alike? At their core, magnetars are neutron stars, the collapsed remnants of massive stars that have exhausted their fuel and exploded in spectacular supernova. But while most neutron stars are already extreme, magnetars take it to another level. Their magnetic fields are so strong that they can distort the very structure of atoms, creating conditions unlike anything else in the cosmos. This immense magnetic energy doesn't just sit quietly. It fuels some of the most dramatic events in the universe, from gamma-ray bursts to starquakes. Gamma-ray bursts, or GRB, are brief but incredibly energetic explosions of light that can outshine an entire galaxy for a few seconds. When a magnetar's magnetic field undergoes a sudden rearrangement, often due to the immense stress it exerts on the star's crust, it can release a torrent of gamma rays. These bursts are so powerful that they can be detected billions of light years away, making them some of the brightest events in the observable universe. But GRBs are just one piece of the puzzle. Magnetars also experience starquakes, violent tremors in their crust caused by the immense strain of their magnetic fields. These quakes can release energy equivalent to a magnitude 32 earthquake. Imagine the entire Earth shaking with the force of 1 billion nuclear bombs. Yet, for all their ferocity, magnetars are incredibly rare. Scientists estimate that only 1 in every 10 neutron stars becomes a magnetar, and their magnetic fields are thought to decay over time, making them even harder to detect. This rarity raises a profound question. What conditions are necessary for a neutron star to become a magnetar? Is it the size of the original star, the way it collapses, or something else entirely? The answers remain elusive, but studying these cosmic powerhouses could shed light on the processes that shape the universe's most extreme objects. What's even more intriguing is the behavior of magnetars when their magnetic fields snap. This phenomenon, known as a magnetic reconnection, occurs when the field lines break and reconnect, releasing a colossal amount of energy. It's as if the magnetar is unleashing a cosmic scream, a burst of radiation so intense it can be detected across vast distances. But what triggers these events, and what happens to the magnetar afterward? The answers could reveal not only the inner workings of these enigmatic stars, but also the fundamental nature of magnetic fields in the universe. As we unravel the mysteries of magnetars, we're reminded of the universe's capacity for both beauty and chaos. These cosmic titans challenge our understanding of physics, pushing the boundaries of what we thought was possible. And as we ponder their secrets, another question arises, one that takes us to the very edge of reality, where the laws of physics may bend in ways we're only beginning to imagine. What lies beyond the reach of a magnetar's magnetic grip, and what other wonders await us in the vast expanse of space? Now, let's explore one of the most intriguing theoretical constructs in the cosmos: white holes. If black holes are the universe's ultimate vacuum cleaners, sucking in everything that crosses their event horizon, white holes are their polar opposite. These hypothetical objects are thought to expel matter and energy into the universe rather than trapping it. Imagine a cosmic fountain, endlessly spewing light and particles into space, defying the very nature of gravity as we know it. But what exactly are white holes, and why do they remain one of the most tantalizing mysteries in astrophysics? The concept of white holes emerges from the equations of general relativity, the same framework that predicts black holes. In fact, white holes are mathematically described as the time-reversed version of black holes. While a black hole's event horizon is a one-way street where matter and energy can enter but never escape, a white hole's event horizon is the opposite: nothing can enter, but everything can exit. It's as if the universe has a cosmic eject button, flinging material into the void. But here's the catch: while black holes have been observed and studied extensively, white holes remain purely theoretical. No direct evidence of their existence has ever been found. So, why haven't we detected white holes? One possibility is that they're incredibly rare or short-lived, making them nearly impossible to observe. Another idea is that they exist in regions of the universe we haven't yet explored, or in forms we don't yet recognize. Some scientists speculate that white holes could be connected to black holes through wormholes, hypothetical tunnels in space-time that link distant points in the universe. In this scenario, a black hole could act as the entrance, while a white hole serves as the exit, creating a cosmic bridge between 2 points in space and time. It's a fascinating idea, but one that raises even more questions. If wormholes exist, could they allow for travel across the universe? And if so, what would that mean for our understanding of reality? The challenge with white holes lies in their theoretical nature. Unlike black holes, which form from the collapse of massive stars, there's no known process that could create a white hole. Some theories suggest they might be remnants of the Big Bang, relics from the universe's fiery birth that have persisted to this day. Others propose that white holes could be the result of quantum fluctuations in space-time, fleeting phenomena that appear and disappear in the blink of an eye. But without observational evidence, these ideas remain speculative, leaving white holes as one of the greatest what-ifs in modern astrophysics. Despite their elusiveness, white holes continue to captivate scientists and science fiction enthusiasts alike. They challenge our understanding of space, time, and the laws of physics, offering a glimpse into what might be possible in the universe's most extreme environments. Could white holes exist somewhere in the cosmos, hidden from our view? And if they do, what secrets might they hold about the nature of reality? As we ponder these questions, we're reminded that the universe is full of mysteries waiting to be uncovered, each one pushing the boundaries of our imagination and our understanding of the cosmos. In the vast expanse of space where the unexpected is the norm, one object stands out as a true enigma. Oumuamua. This mysterious visitor, the first known interstellar object to pass through our solar system, arrived in October 2017, sparking a wave of excitement and speculation among astronomers and the public alike. Unlike anything we've seen before, Oumuamua defied easy categorization, leaving scientists scratching their heads and fueling debates that continue to this day. What made Oumuamua so extraordinary was its unique shape and behavior. Most asteroids and comets in our solar system are roughly spherical or irregular, but Oumuamua was different. Observations suggested it was elongated, shaped like a cigar or a pancake, with a length up to 10 times its width. This unusual form was just the beginning of the mystery. As it traveled through our solar system, Oumuamua exhibited unexpected acceleration, speeding up in a way that couldn't be explained by gravity alone. This strange behavior led to a flurry of theories, each more intriguing than the last. At first, scientists thought Oumuamua might be a comet. Comets, after all, are known to accelerate as they release gas and dust when heated by the sun. But there was no visible coma, the cloud of gas and dust that typically surrounds a comet's nucleus. Without this telltale sign, the comet theory began to unravel. Next, some proposed it was an asteroid, but its acceleration didn't fit the profile of a typical rocky body. So, if it wasn't a comet or an asteroid, what was it? This uncertainty opened the door to more imaginative ideas. One hypothesis put forward by Harvard astronomer Avi Loeb suggested that Oumuamua could be a piece of alien technology, a light sail propelled by the pressure of sunlight, or perhaps even a derelict spacecraft. While this idea captured the public's imagination, most scientists remained skeptical, pointing out that natural explanations, though still elusive, are far more likely. For instance, some researchers have proposed that Oumuamua could be a fragment of a larger object, torn apart by a cataclysmic event in its home system. Others suggest it might be made of exotic materials like hydrogen ice, which could explain its acceleration without leaving a visible trail. Despite the many theories, Oumuamua's true nature remains a mystery. By the time we detected it, it was already speeding away, leaving us with only a brief window to study it. The data we collected has been scrutinized endlessly, but the answers remain just out of reach. What we do know is that Oumuamua came from another star system, making it a messenger from the depths of interstellar space. But what message was it carrying? Was it a fragment of a distant planet, a wandering comet, or something entirely beyond our current understanding? As we ponder the possibilities, one thing is certain: Oumuamua has forever changed the way we think about the universe. It reminds us that there's so much we don't know, and that the cosmos is full of surprises waiting to be discovered. And as we turn our gaze to the next mystery, we're left with a lingering question. What other interstellar visitors might be out there, silently drifting through the void, waiting to reveal their secrets? As we journey deeper into the cosmos, we encounter a realm of worlds so diverse and extraordinary that they seem to defy imagination, the strange and fascinating domain of exoplanets. These are planets that orbit stars beyond our solar system, and they come in every conceivable variety. From scorching lava worlds to glittering diamond planets, the universe is a cosmic tapestry woven with countless planetary possibilities. Each discovery challenges our understanding of what a planet can be and pushes the boundaries of our cosmic curiosity. Take, for instance, the enigmatic class of planets known as hot Jupiters. These gas giants are similar in size to Jupiter but orbit incredibly close to their host stars, completing a full revolution in just days or even hours. The result, surface temperatures that soar to thousands of degrees Celsius, creating atmospheres so hot they could vaporize metal. How these planets formed so close to their stars remains a puzzle, as traditional models of planetary formation suggest they should have originated much farther out. Are they the product of violent cosmic collisions, or did they migrate inward over time? The answers could rewrite the rules of how planets are born. Then there are the super-Earths, rocky planets larger than Earth but smaller than Neptune. These worlds occupy a mysterious middle ground with compositions that could range from dense, molten rock to thick, steamy atmospheres. Some super-Earths may even harbor oceans of water, raising the tantalizing possibility of habitability. But with such a wide range of potential environments, could life as we know it exist on these distant worlds? Or might they host entirely new forms of life, adapted to conditions we can barely imagine? Among the most bizarre exoplanets are the so-called diamond planets. These worlds are thought to be rich in carbon, with extreme pressures causing the element to crystallize into diamond. Imagine a planet where mountains of diamond rise above molten seas of carbon, a truly alien landscape. Equally astonishing are the lava worlds, where the surface is a molten ocean of rock, constantly churning under the heat of a nearby star. These extreme environments remind us that the universe is far stranger and more varied than we ever imagined. But perhaps the most exciting aspect of exoplanet research is the search for Earth-like worlds, planets that could potentially support life as we know it. Scientists have identified several candidates within the habitable zone, the region around a star where temperatures are just right for liquid water to exist. Could one of these worlds be Earth 2.0, a planet with conditions similar to our own, teeming with life? The discovery of such a world would be a monumental moment in human history, reshaping our understanding of our place in the cosmos. As we continue to explore these distant worlds, we're reminded of the sheer diversity and complexity of the universe. Each exoplanet offers a new piece of the cosmic puzzle, challenging our assumptions and expanding our horizons. From fiery gas giants to glittering carbon worlds, the possibilities are as endless as the stars themselves. And as we turn our gaze to the next mystery, we're left with a profound question. What other wonders lie hidden among the stars waiting to be discovered? Could the ultimate discovery, a world like our own, be just beyond the horizon? Now, let's unravel one of the most mind-bending concepts in theoretical physics: cosmic strings. Imagine the universe as a vast, intricate tapestry woven together by the threads of space and time. Cosmic strings are thought to be tiny, one-dimensional defects in this fabric, remnants from the earliest moments of the cosmos. These hypothetical structures are so thin, yet so dense, that they could stretch across the entire universe, carrying unimaginable amounts of energy. But what exactly are cosmic strings, and why do they captivate the imagination of physicists and cosmologists alike? Cosmic strings are believed to have formed during the infancy of the universe, just fractions of a second after the Big Bang. During this chaotic period, the universe underwent a series of phase transitions, much like water freezing into ice but on a cosmic scale. As the universe cooled, these transitions could have created cracks or tears in the fabric of space-time, giving rise to cosmic strings. Think of them as the cosmic equivalent of cracks in ice, but instead of breaking apart, they're threads of pure energy, threading through the cosmos like invisible wires. One of the most intriguing aspects of cosmic strings is their potential to explain anomalies in the cosmic microwave background, or CMB. This faint glow of radiation is the oldest light in the universe, a snapshot of the cosmos just 380,000 years after the Big Bang. Within this ancient light, scientists have detected subtle irregularities, tiny temperature fluctuations that hint at the universe's early structure. Could these irregularities be the fingerprints of cosmic strings? Some researchers believe that the gravitational influence of these strings could have imprinted their signature on the CMB, offering a tantalizing clue to their existence. But cosmic strings aren't just relics of the past, they might also shape the future of the universe. One of their most fascinating properties is their ability to produce gravitational waves, ripples in space-time caused by massive cosmic events. Unlike the gravitational waves generated by black hole mergers or neutron star collisions, those from cosmic strings would be continuous, like the hum of a cosmic violin. Detecting these waves could provide direct evidence of cosmic strings, opening a new window into the universe's earliest moments. What makes this idea even more compelling is the possibility that cosmic strings could still exist today, lurking in the depths of space. If they're out there, their immense gravitational fields could bend light, distorting the images of distant galaxies in a phenomenon known as gravitational lensing. Some astronomers are already searching for these telltale distortions, hoping to catch a glimpse of these elusive threads. But so far, cosmic strings remain just beyond our reach, a tantalizing mystery waiting to be solved. Could these one-dimensional defects be the threads weaving the fabric of the universe? The answer lies hidden in the vast expanse of space, waiting to be uncovered by the next generation of telescopes and detectors. As we continue to explore this cosmic enigma, we're reminded that the universe is full of surprises, each one challenging our understanding of reality and pushing the boundaries of what we thought was possible. And as we turn our gaze to the next mystery, we'll delve into another phenomenon that stretches the limits of our imagination, one that could reshape our understanding of the cosmos in ways we're only beginning to grasp. Now, let's turn our attention to one of the most explosive and enigmatic phenomena in the cosmos: gamma-ray bursts. These are the most energetic events known to occur in the universe, releasing in mere seconds more energy than our Sun will emit over its entire 10 billion-year lifespan. To put it into perspective, a single gamma-ray burst can outshine an entire galaxy, making them some of the brightest flashes of light in the observable universe. But what causes these colossal explosions, and why do they remain one of the most unpredictable and mysterious events in space? Gamma-ray bursts, or GRB, come in two main types: short and long. Short bursts last less than 2 seconds and are thought to originate from the collision of neutron stars, the ultra-dense remnants of massive stars. When these stellar corpses spiral into each other, they unleash a cataclysmic explosion, sending ripples of gravitational waves through space and a torrent of gamma rays across the cosmos. Long bursts, on the other hand, can last from a few seconds to several minutes and are believed to result from the collapse of massive stars into black holes. As the star's core implodes, it launches jets of energy at nearly the speed of light, piercing through the outer layers of the star and erupting into space as a gamma-ray burst. What makes these events so fascinating and so baffling is their unpredictability. Gamma-ray bursts appear randomly across the sky with no warning or pattern. One moment, the universe is quiet; the next, an unimaginable explosion lights up the void. This randomness makes them incredibly difficult to study, as we never know where or when the next burst will occur. To catch these fleeting events, astronomers rely on networks of satellites and telescopes, constantly scanning the skies for the telltale flash of gamma rays. When a burst is detected, it triggers a global effort to observe it across the electromagnetic spectrum, from radio waves to X-rays, in the hopes of unraveling its secrets. But the mystery doesn't end with the burst itself. In the aftermath of a gamma-ray burst, something equally intriguing often appears, an afterglow. This lingering emission, which can last for days or even weeks, is thought to be caused by the burst jets colliding with surrounding gas and dust. The afterglow provides crucial clues about the burst's environment and origins, but it also raises new questions. Why do some bursts produce such bright afterglows while others fade almost immediately? What determines the structure and behavior of the jets? These are puzzles that scientists are still working to solve. The sheer power of gamma-ray bursts also has profound implications for life in the universe. If a burst were to occur too close to a planet within a few thousand light years, its intense radiation could strip away the ozone layer, exposing the surface to deadly ultraviolet rays from its star. It's a sobering thought. A single cosmic explosion could sterilize an entire world, extinguishing any chance of life. Yet, despite their destructive potential, gamma-ray bursts also serve as cosmic lighthouses, illuminating the distant reaches of the universe and allowing us to peer back in time to some of the earliest moments after the Big Bang. So, what causes these cosmic explosions? Is it the violent death of a star, the collision of neutron stars, or something even more exotic? The answers lie hidden in the depths of space, waiting to be uncovered by the next generation of observatories and instruments. As we continue to study these enigmatic events, we're reminded of the universe's capacity for both creation and destruction, a delicate balance that shapes the cosmos in ways we're only beginning to understand. And as we ponder the mysteries of gamma-ray bursts, another question arises. What other cosmic phenomena might be lurking in the shadows, waiting to reveal their secrets? Now let's delve into one of the most perplexing cosmic mysteries, the Great Attractor. Imagine a force so powerful that it's tugging entire galaxies, including our own Milky Way, through the vastness of space. This isn't science fiction. It's a real gravitational anomaly located roughly 250 million light-years away, hidden behind the dense plane of our galaxy. The Great Attractor is a cosmic enigma, a region of space that exerts an irresistible pull, drawing galaxies toward it at astonishing speeds. But what exactly is it, and why is it so difficult to study? The challenge lies in its location. The Great Attractor sits in a part of the sky obscured by the Milky Way's disk, a region packed with stars, gas, and dust. This galactic zone of avoidance makes it nearly impossible to observe directly using visible light. It's like trying to peer through a dense fog, only the faintest glimpses of what lies beyond are visible. To overcome this, astronomers rely on other wavelengths such as radio and X-rays to pierce through the obscuring material and map the hidden structures behind it. What they've discovered is both fascinating and baffling. One leading theory suggests that the Great Attractor is a massive cluster of galaxies, a cosmic heavyweight with enough gravitational pull to influence the motion of everything around it. This cluster, known as the Norma cluster, contains thousands of galaxies bound together by their mutual gravity. But while this cluster is undeniably massive, it may not be massive enough to fully explain the Great Attractor's pull. Could there be something even larger lurking in the shadows, something we haven't yet detected? Another possibility is dark matter. This mysterious substance, which makes up most of the universe's mass, could be concentrated in the region of the Great Attractor, amplifying its gravitational influence. If true, this would mean that the Great Attractor isn't just a cluster of galaxies, but a vast reservoir of dark matter, shaping the motion of galaxies on a cosmic scale. But dark matter, by its very nature, is invisible, making it incredibly difficult to confirm this hypothesis. What's even more intriguing is the idea that the Great Attractor might not be the final destination. Beyond it lies an even larger structure known as the Shapley supercluster, a colossal collection of galaxies that could be exerting its own gravitational pull. Some scientists believe that the Great Attractor is merely a stepping stone in a much larger cosmic flow, with galaxies being drawn toward an even greater gravitational force. This raises a profound question. What lies at the heart of the Great Attractor, and what role does it play in the grand dance of the universe? As we continue to probe this cosmic mystery, we're reminded of how much we still have to learn about the universe. The Great Attractor challenges our understanding of gravity, dark matter, and the large-scale structure of the cosmos. It's a reminder that even in the vastness of space, there are forces at work that we're only beginning to comprehend. And as we turn our gaze to the next mystery, we're left with a tantalizing thought. What other hidden wonders might be shaping the universe, waiting to be uncovered? Let's shift our focus to one of the Milky Way's most astonishing features, the Fermi bubbles. These colossal structures are like two enormous balloons of gamma-ray energy, stretching tens of thousands of light-years above and below the galactic plane. Picture a pair of cosmic hourglasses glowing faintly with high-energy radiation, yet invisible to the naked eye. Discovered in 2010 by NASA's Fermi Gamma-Ray Space Telescope, these bubbles have become one of the most intriguing puzzles in modern astrophysics. But what exactly are they, and how did they form? The Fermi bubbles are immense. Each one spans roughly 25,000 light-years, making them nearly as tall as the Milky Way itself. They're filled with superheated gas, magnetic fields, and high-energy particles, emitting gamma rays that reveal their presence. But here's the twist: their origins remain a mystery. The most widely accepted theory suggests they were created by a massive eruption from the supermassive black hole at the center of our galaxy, Sagittarius A. This eruption, which may have occurred millions of years ago, could have blasted out jets of energy and matter, inflating these gigantic bubbles over time. It's as if our galaxy's heart once roared with unimaginable power, leaving behind these ghostly echoes. Yet not everyone is convinced. Some scientists propose alternative explanations, such as a burst of star formation in the galactic core. When massive stars are born and die in rapid succession, they can release enormous amounts of energy, potentially inflating structures like the Fermi bubbles. Others suggest that the bubbles could be the result of dark matter annihilation, a process where particles of dark matter collide and release energy. Each theory offers a tantalizing glimpse into the forces shaping our galaxy, but none have been definitively proven. The Fermi bubbles remain a cosmic riddle, challenging us to rethink what we know about galactic behavior. What makes these structures even more fascinating is their potential to teach us about galactic evolution. The energy required to create the Fermi bubbles is staggering, hinting at a period of intense activity in the Milky Way's history. If they were indeed formed by a black hole eruption, it would suggest that our galaxy's core is far more dynamic than we once thought. These bubbles could be a snapshot of a violent, transformative event, one that shaped the Milky Way into the spiral we see today. But how often do such eruptions occur? And what triggers them? The answers could help us understand not just our own galaxy, but the behavior of galaxies across the universe. So, what caused these colossal bubbles? Was it the fury of a supermassive black hole, the birth and death of countless stars, or something entirely unexpected? As we continue to study these enigmatic structures, we're reminded that even our home galaxy holds secrets we're only beginning to uncover. The Fermi bubbles are a testament to the universe's capacity for both beauty and chaos, and they invite us to explore the next mystery, one that takes us even deeper into the heart of the cosmos. In the vast silence of space, where the hum of cosmic noise fills the void, one signal stands out as a beacon of mystery: the WOW signal. Detected on August 15, 1977, by the Big Ear radio telescope at Ohio State University. This brief but powerful burst of radio waves has become one of the most tantalizing enigmas in the search for extraterrestrial intelligence. Lasting just 72 seconds, the signal was so unusual that astronomer Jerry Amon, who first spotted it in the data, circled the reading in red ink and scribbled, "Wow." Next to it, a name that has stuck ever since. But what made this signal so extraordinary, and why does it continue to captivate scientists and dreamers alike? The WOW signal was unlike anything astronomers had ever encountered. It originated from the direction of the constellation Sagittarius, near the star Chi Sagittarii, and had a frequency of 1,420 MHz, a range that's particularly significant because it's close to the hydrogen line, a frequency often considered a likely channel for interstellar communication. Hydrogen, after all, is the most abundant element in the universe, and any advanced civilization might use it to send a cosmic hello. The signal was also incredibly strong, far exceeding the typical background noise of space, and it appeared to be narrowband, a characteristic that suggests an artificial origin rather than a natural cosmic event. Despite its brief duration, the WOW signal has sparked decades of speculation and debate. Could it have been a message from an alien civilization, intentionally or unintentionally broadcast into the cosmos? Or was it something else entirely, a natural phenomenon we've yet to fully understand? Over the years, numerous explanations have been proposed, from comets and asteroids to satellite interference, but none have fully accounted for the signal's unique characteristics. The mystery deepens when you consider that the signal has never been detected again, despite repeated efforts to scan the same region of space. It's as if the universe sent us a single, fleeting clue, one that we've been trying to decipher ever since. The search for the source of the WOW signal continues to this day, driven by advancements in technology and the enduring hope of finding evidence of extraterrestrial intelligence. Modern radio telescopes, with their unparalleled sensitivity and precision, are scanning the skies in hopes of detecting a signal similar to the WOW event. Projects like the Breakthrough Listen initiative are dedicating thousands of hours to the search, analyzing vast swaths of the electromagnetic spectrum for any sign of intelligent life. Yet, for all our efforts, the WOW signal remains an isolated incident, a tantalizing hint that we're not alone, but one that refuses to reveal its secrets. What makes the WOW signal so compelling is not just its mystery, but what it represents. It's a reminder of how little we know about the universe and the possibilities that lie beyond our understanding. Could it have been a deliberate attempt at communication, a cosmic beacon meant to catch our attention? Or was it simply a fluke, a rare and fleeting event that we happened to catch at the right time? The truth may remain elusive, but the WOW signal continues to inspire us to keep searching, to keep listening, and to keep wondering about the infinite possibilities that await us in the cosmos. So, was the WOW signal a message from another civilization? As we ponder this question, we're reminded that the universe is full of mysteries waiting to be uncovered, each one a potential clue to the greatest question of all: are we alone? And as we turn our gaze to the next mystery, we're left with a sense of anticipation, eager to explore what other cosmic enigmas might be waiting to reveal themselves. Far beyond the familiar planets of our solar system lies a realm of icy wonders, the Kuiper belt. Stretching out past Neptune, this vast region is home to countless frozen bodies, remnants of the solar system's earliest days. Think of it as a cosmic freezer, preserving fragments of the past that hold clues to how our planetary neighborhood came to be. But the Kuiper belt isn't just a relic of history. It's a dynamic frontier filled with mysteries waiting to be unraveled. At the heart of this icy expanse are some of the solar system's most intriguing objects. Pluto, once considered the ninth planet, reigns as the Kuiper belt's most famous resident. But it's not alone. Eris, another dwarf planet, rivals Pluto in size and even sparked the debate that led to Pluto's reclassification. These distant worlds, along with countless smaller bodies, are more than just frozen rocks. They're time capsules holding secrets about the solar system's formation over 4.5 billion years ago. The Kuiper belt's icy inhabitants are thought to be the building blocks of planets, leftover material from the swirling disk of gas and dust that gave birth to the Sun and its family of worlds. Studying these objects offers a glimpse into the chaotic early days of the solar system, when collisions and gravitational tugs shaped everything we see today. But the Kuiper belt isn't just a museum of the past, it's also a place of surprises. The discovery of Pluto's heart-shaped glacier, for instance, revealed a world far more complex and geologically active than anyone had imagined. In 2015, NASA's New Horizons mission provided humanity's first close-up look at Pluto, transforming it from a distant speck of light into a world of stunning diversity. Towering mountains of water ice, vast plains of frozen nitrogen, and a hazy blue atmosphere painted a picture of a dynamic and evolving world. New Horizons didn't stop there after its Pluto flyby. It ventured deeper into the Kuiper belt, encountering Arakoth, a peculiar snowman-shaped object. This ancient relic, untouched by the chaos of planetary formation, offered a pristine snapshot of the solar system's infancy. Yet, for all we've learned, the Kuiper belt remains a place of profound mystery. Its largest objects, like Pluto and Eris, challenge our understanding of what defines a planet. The region's icy bodies, some of which may harbor hidden oceans, raise questions about the potential for life in the most unexpected places. And the sheer scale of the Kuiper belt, stretching billions of miles into space, means there's still so much we haven't discovered. What secrets does the Kuiper belt hold? Could there be more dwarf planets lurking in its depths, or even objects larger than Pluto waiting to be found? As we continue to explore this distant frontier, we're reminded that the solar system is far more complex and wondrous than we ever imagined. And as we peer into the icy shadows of the Kuiper belt, another cosmic mystery beckons, one that takes us even farther into the depths of space where the unknown awaits. Beyond the Kuiper belt, far past the orbits of Neptune and Pluto, lies a region so vast and remote that it stretches the limits of our imagination, the Oort cloud. This hypothetical shell of icy objects is thought to encircle the entire solar system, a cosmic reservoir of comets and frozen debris left over from the birth of our sun and planets. Imagine a cloud so immense that it extends nearly halfway to the nearest star, a boundary marking the edge of our sun's gravitational influence. It's a place where the solar system's story begins, and yet it remains one of the most elusive frontiers in astronomy. The Oort cloud is believed to be the birthplace of long-period comets, those spectacular visitors that grace our skies once every few thousand years. Unlike their short-period cousins, which originate in the Kuiper belt, long-period comets follow wild, elongated orbits that take them far beyond the planets before swinging back toward the sun. These icy travelers are thought to be nudged out of the Oort cloud by gravitational disturbances, perhaps from passing stars or the gravitational tug of the Milky Way itself. When they plunge into the inner solar system, they bring with them pristine material from the solar system's earliest days, offering a glimpse into the raw ingredients that formed our cosmic neighborhood. But studying the Oort cloud is no easy task. Its objects are incredibly distant, so far away that even our most advanced telescopes struggle to detect them. The closest edge of the Oort cloud is estimated to be about 2,000 times farther from the Sun than Pluto, with its outer reaches extending up to a staggering 100,000 times that distance. This vast expanse makes direct observation nearly impossible, leaving scientists to rely on indirect evidence such as the trajectories of long-period comets to map its structure and composition. One of the most tantalizing mysteries of the Oort cloud is the possibility of undiscovered worlds lurking within its icy depths. Some astronomers speculate that the gravitational influence of a hidden planet, perhaps a Planet 9, could explain the peculiar orbits of certain distant objects in the Kuiper belt and beyond. This hypothetical planet, if it exists, would be a cold, dark world, orbiting so far from the Sun that it might take tens of thousands of years to complete a single trip around our star. Could the Oort cloud be hiding such a planet, or even multiple worlds, waiting to be discovered? The idea fuels both scientific curiosity and the imagination, suggesting that our solar system's story may still have untold chapters. What makes the Oort cloud even more fascinating is its role as a cosmic time capsule. The objects within it have remained largely unchanged since the solar system's formation over 4.5 billion years ago, preserving a record of the conditions that gave rise to the Sun and its family of planets. By studying the comets that originate here, scientists can piece together the early history of our solar system and better understand how other star systems might form. But the Oort cloud's remoteness means that much of its story remains shrouded in mystery. Could this distant cloud of ice and dust hold the key to understanding our solar system's origins, or even harbor undiscovered worlds? As we peer into the depths of this enigmatic region, we're reminded that the universe is full of surprises, each one challenging our assumptions and expanding our horizons. And as we turn our gaze to the next mystery, we're left with a lingering question. What other secrets might be waiting to be uncovered in the farthest reaches of space? As we journey through the cosmos, even our most advanced spacecraft can encounter phenomena that defy explanation. One such mystery emerged from the depths of our solar system, where the Pioneer 10 and Pioneer 11 probes, launched in the early 1970s, began behaving in a way that left scientists scratching their heads. This unexpected behavior became known as the Pioneer Anomaly, a subtle but persistent deceleration that couldn't be explained by the known laws of physics. It was as if the universe itself was gently tugging on these spacecraft, slowing them down in ways that challenged everything we thought we knew about gravity and motion. The anomaly was first noticed in the 1980s when scientists tracking the probe's trajectories found that they were slowing down ever so slightly, just a few nanometers per second squared. While this might seem negligible over the vast distances of space, even the tiniest discrepancy can add up, throwing off calculations and raising questions. What could be causing this mysterious drag? At first, some speculated it might be a sign of new physics, perhaps a flaw in our understanding of gravity, or even the influence of dark matter. The idea that the universe might have hidden forces at work was both thrilling and unsettling, opening the door to a host of possibilities. As researchers dug deeper, however, a more mundane explanation began to emerge. One leading theory suggested that the anomaly could be caused by thermal radiation heat emitted unevenly from the spacecraft's power sources, creating a tiny but consistent push in the opposite direction of their motion. This heat radiating off the probe's surfaces might have acted like a faint but steady brake, slowing them down over time. By the 2010s, detailed analysis of the spacecraft's design and thermal properties seemed to confirm this explanation, effectively solving the mystery. Yet the Pioneer anomaly left a lasting legacy, reminding us that even our most precise instruments can encounter unexpected challenges in the harsh environment of space. The resolution of the Pioneer anomaly was a victory for science, but it also highlighted the importance of curiosity and meticulous investigation. Without the initial intrigue sparked by the anomaly, we might never have taken such a close look at the thermal properties of spacecraft or considered how even the smallest forces could influence their trajectories. This episode serves as a powerful reminder that anomalies, no matter how small, can lead to valuable insights and improvements in our understanding of the cosmos. But what other anomalies might be lurking in the depths of space, waiting to challenge our assumptions and push the boundaries of our knowledge? As we continue to explore the universe, we're bound to encounter more mysteries, some of which might require entirely new ways of thinking to solve. The Pioneer anomaly may have been resolved, but it stands as a testament to the fact that the universe is full of surprises, each one an opportunity to learn and grow. And as we turn our attention to the next mystery, we're reminded that the journey of discovery is far from over. There's always more to explore, more to question, and more to uncover in the vast expanse of the cosmos. Imagine the universe as a vast, intricate tapestry, woven together by threads of matter and energy stretching across billions of light years. This is the cosmic web, a colossal network of dark matter and gas filaments that forms the backbone of the cosmos. It's not just a structure, it's the scaffolding upon which galaxies are built, the hidden framework that shapes the universe as we know it. But how did this cosmic web come to be, and what role does it play in the grand story of the universe? At the heart of the cosmic web lies dark matter, the invisible glue that holds everything together. Though we can't see it directly, its gravitational influence is undeniable. Dark matter's pull draws ordinary matter, gas, dust, and eventually galaxies into its web-like structure, creating vast filaments that stretch across the cosmos. These filaments intersect at dense nodes where galaxies cluster together, forming the universe's largest structures. Without the cosmic web, galaxies would be scattered randomly, adrift in the void. Instead, they are organized into a breathtaking network, a cosmic blueprint that guides the evolution of the universe. Mapping the cosmic web is no small feat. To trace its invisible threads, astronomers rely on quasars, the brilliant beacons of light we discussed earlier. These distant objects act like cosmic lighthouses, their light traveling through the web's filaments before reaching us. As this light passes through the gas within the filaments, it leaves behind subtle fingerprints in the form of absorption lines. By analyzing these lines, scientists can map the distribution of gas and dark matter, piecing together the web's intricate structure. It's a bit like using X-rays to see the bones beneath the skin, except here, the bones are made of dark matter and the skin is the fabric of space-time itself. But the cosmic web isn't just a static structure, it's a dynamic, evolving entity. In the early universe, just moments after the Big Bang, tiny fluctuations in density set the stage for the web's formation. Over billions of years, gravity amplified these fluctuations, pulling matter into the filaments and nodes we see today. This process is still ongoing, with the web continuing to grow and change as galaxies collide, merge, and drift apart. Yet, many questions remain. Why does the web take on this particular structure? What drives its evolution, and how does it influence the formation of galaxies and stars? One of the most compelling mysteries surrounding the cosmic web is its connection to the universe's largest scale structures. The web's filaments don't just connect galaxies, they also link galaxy clusters, superclusters, and even the voids, the vast, empty regions between the filaments. These voids are just as important as the filaments themselves, acting as cosmic pressure points that shape the web's growth. Together, the filaments and voids create a delicate balance, a cosmic dance that has been unfolding since the dawn of time. So, is the cosmic web the blueprint of the universe? Does it hold the key to understanding how galaxies, stars, and even life itself came to be? As we continue to study this vast network, we're reminded that the universe is far more interconnected than we ever imagined. And as we turn our gaze to the next mystery, we'll explore another phenomenon that blurs the line between the known and the unknown, a mystery that could reshape our understanding of the cosmos in ways we're only beginning to grasp. Now, let's dive into one of the most pressing puzzles in modern cosmology, the Hubble tension. This mystery centers on a discrepancy that's shaking the foundations of our understanding of the universe, the rate at which it's expanding. For decades, scientists have used two primary methods to measure this expansion rate, known as the Hubble constant. The first relies on observations of nearby objects like Cepheid variable stars and supernova to calculate how fast the universe is stretching. The second method uses the cosmic microwave background, the faint afterglow of the Big Bang, to infer the expansion rate from the early universe, the problem. These two methods don't agree. They're giving us different answers, and the gap between them is significant enough to keep cosmologists up at night. At first glance, this might seem like a small technical hiccup, but the Hubble tension has far-reaching implications. It's not just about numbers on a chart, it's about our fundamental understanding of how the universe works. If the discrepancy is real and not due to some error in measurement, it could mean that our current model of cosmology, the so-called standard model, is missing something crucial. This model, which includes dark energy, dark matter, and the Big Bang, has been remarkably successful in explaining the universe's behavior, but the Hubble tension suggests there might be more to the story. Could there be unknown forces at play, or perhaps new particles or fields that we haven't yet discovered? One intriguing possibility is that dark energy, the mysterious force driving the universe's accelerated expansion, isn't as constant as we've assumed. What if it's changing over time, subtly influencing the expansion rate in ways we haven't accounted for? This idea, known as dynamic dark energy, could help resolve the tension by introducing a variable that adjusts the expansion rate at different points in the universe's history. Another theory involves exotic particles or interactions that could be altering the way the universe evolves. These hypothetical particles wouldn't just tweak the Hubble constant. They might also explain other cosmic mysteries, like the nature of dark matter or the behavior of neutrinos. The stakes are high. If the Hubble tension forces us to revise our understanding of the universe, it could lead to a revolution in physics. We might need to rethink everything from the Big Bang to the ultimate fate of the cosmos. But for now, the tension remains unresolved, a tantalizing puzzle that challenges our most brilliant minds. Could it be a sign that we're on the verge of a groundbreaking discovery? Or is it simply a reminder of how much we still have to learn? As we grapple with this mystery, another question looms large. What other surprises might the universe have in store? The Hubble tension isn't just a scientific problem. It's an invitation to explore, to question, and to imagine. And as we turn our attention to the next cosmic enigma, we're reminded that the universe is always one step ahead, daring us to keep up with its endless mysteries. Could the Hubble tension be the key to unlocking a deeper understanding of reality itself? Only time, and perhaps a few more groundbreaking observations, will tell. When we think of the universe's mysteries, we often focus on the exotic and the invisible dark matter, dark energy, black holes. But there's another puzzle hiding in plain sight, one that involves the very stuff we're made of, ordinary matter. You might be surprised to learn that about half of the universe's baryonic matter, the protons, neutrons, and electrons that make up stars, planets, and even us, is missing. That's right, despite our best efforts, a significant portion of the universe's ordinary matter is unaccounted for, and this mystery has left scientists scratching their heads for decades. So, where is it all hiding? The answer may lie in a cosmic reservoir known as the Warm-Hot Intergalactic Medium, or WIM. This diffuse network of gas filaments stretches between galaxies, filling the vast voids of space with a faint, almost ghostly presence. Unlike the cold gas clouds we're familiar with, the WIM is incredibly hot, millions of degrees hot, and so tenuous that it's nearly invisible to traditional telescopes. Detecting it requires looking for subtle clues, like the way it absorbs light from distant quasars or emits faint X-rays. These observations suggest that the WIM could be the hiding place for the missing baryons, a cosmic treasure trove of matter that's been overlooked simply because it's so hard to see. But why is this matter so elusive? One reason is its temperature. The WIM is too hot to glow brightly in visible light, yet not hot enough to emit strong X-rays. It's like trying to spot a faint ember in a dark room. You know it's there, but it's nearly impossible to see. Another challenge is its distribution. The WIM isn't concentrated in neat, dense clouds. Instead, it's spread out in a delicate web-like structure, making it even harder to detect. This combination of temperature and distribution has kept the missing baryons hidden in plain sight, blending into the cosmic background like a chameleon. The implications of this mystery go far beyond just accounting for missing matter. The WIM isn't just a cosmic storage unit, it's a vital part of the universe's structure. These filaments of hot gas act as the scaffolding for galaxy formation, guiding the flow of matter and energy across the cosmos. Without them, galaxies might never have formed, and the universe as we know it would look very different. Understanding the WIM could help us piece together the story of how the universe evolved from a smooth, uniform soup of particles into the intricate web of galaxies and clusters we see today. Yet, even as we begin to unravel the mystery of the missing baryons, questions remain. How did this matter end up in the WIM, and what processes keep it there? Could there be other reservoirs of baryonic matter we haven't yet discovered? And perhaps most intriguingly, what does this missing matter tell us about the universe's overall composition and evolution? The search for answers is far from over, but each discovery brings us closer to understanding the true nature of the cosmos. So, where are the universe's missing baryons hiding? As we continue to probe the depths of space, we're reminded that even the most familiar aspects of the universe can hold profound mysteries. The WIM may be elusive, but it's also a testament to the universe's complexity, a reminder that there's always more to explore, more to uncover, and more to wonder about in the vast expanse of space. And as we turn our gaze to the next cosmic enigma, we're left with a sense of anticipation, eager to see what other secrets the universe might reveal. Now, let's turn our attention to one of the most perplexing anomalies in the cosmic microwave background, the CMB cold spot. This mysterious region, spanning nearly 2 billion light-years across, stands out as an unusually cold patch in the otherwise uniform sea of ancient light that fills the universe. It's like finding a frosty fingerprint on the fabric of space-time, a subtle but undeniable deviation from the expected. But what could cause such a vast and frigid anomaly, and what does it tell us about the universe's hidden secrets? The cosmic microwave background, or CMB, is the afterglow of the Big Bang, a snapshot of the universe when it was just 380,000 years old. This faint radiation is remarkably uniform, with only tiny fluctuations in temperature that reveal the seeds of galaxies and galaxy clusters. Yet the cold spot is different. Its temperature is significantly lower than its surroundings, a discrepancy that has puzzled scientists since its discovery in 2004. At first glance, it might seem like a minor blip in the data, but its sheer size and stark contrast make it a cosmic oddity that demands explanation. One leading theory suggests the cold spot could be a supervoid, an enormous, sparsely populated region of space where the density of matter is far lower than average. In such a void, light traveling through would lose energy as it climbs out of the gravitational well, an effect known as the integrated Sachs-Wolfe effect. This energy loss could explain the colder temperature observed in the CMB. However, the sheer scale of the cold spot challenges this idea. Could a void really be that large, or is something even more exotic at play? This is where things get truly fascinating. Some researchers have proposed that the cold spot might be evidence of a collision with another universe. According to this bold hypothesis, our universe could be part of a multiverse, a vast collection of parallel realities, each with its own physical laws. If another universe brushed against ours in the distant past, the interaction might have left behind a kind of cosmic bruise, manifesting as the cold spot. It's a mind-bending idea, one that challenges our understanding of reality and opens the door to infinite possibilities. The implications of the cold spot are profound. If it truly is a sign of a multiverse, it could revolutionize our understanding of existence itself. It would mean that our universe is just one of countless others, each with its own unique properties and histories. The cold spot could be a rare glimpse into this cosmic tapestry, a hint that there's far more to reality than we've ever imagined. But for now, the evidence remains inconclusive and the mystery persists. Could the cold spot be a window into another reality, a tantalizing clue to the existence of a multiverse? As we ponder this question, we're reminded that the universe is full of surprises, each one challenging our assumptions and expanding our horizons. And as we turn our gaze to the next cosmic enigma, we're left with a sense of wonder, eager to explore what other mysteries might be waiting to reveal themselves in the vast expanse of space. Let's journey to the heart of our galaxy, a place of unimaginable energy and mystery, the Milky Way's galactic center. This region, located about 26,000 light-years from Earth, is a cosmic maelstrom, teeming with activity that defies comprehension. At its core lies Sagittarius A, a supermassive black hole with a mass equivalent to 4 million suns. Surrounding it is a chaotic dance of stars, gas clouds, and other celestial objects, all swirling in the grip of its immense gravity. Yet, for all its power, the galactic center holds secrets that even the most advanced telescopes struggle to unravel. One of the most puzzling features of the galactic center is its dense star clusters. These tightly packed groups of stars, known as nuclear star clusters, orbit perilously close to Sagittarius A. Some stars whip around the black hole at speeds exceeding thousands of kilometers per second, their trajectories bending sharply under its gravitational pull. But how did these stars end up so close to such a destructive force? One theory suggests they were born in the intense environment near the black hole, forming from gas clouds compressed by its gravity. Another possibility is that they migrated inward over time, drawn by the black hole's inexorable pull. Whatever their origin, these stars challenge our understanding of how stellar systems form and evolve in extreme conditions. Adding to the intrigue is the strange behavior of objects near Sagittarius A. Take, for instance, the star S2, which orbits the black hole in a highly elliptical path. Every 16 years, it makes a close approach, skimming just 17 light hours from the event horizon. During these encounters, S2 experiences extreme gravitational forces, its light stretched and distorted by the black hole's immense gravity. Observations of S2 have provided some of the strongest evidence for the existence of supermassive black holes, but they've also raised new questions. Why do some stars survive such close encounters while others are torn apart? And what happens to the material that gets too close, vanishing into the black hole's inscrutable depths? But the mysteries don't stop there. The galactic center is also a hotspot for possible dark matter annihilation. Dark matter, the invisible substance that makes up most of the universe's mass, is thought to be densely concentrated near the black hole. As particles of dark matter collide and annihilate, they could produce bursts of gamma rays, a signature that astronomers are searching for. If detected, this would be a groundbreaking discovery, offering a glimpse into the nature of one of the universe's greatest enigmas. Yet, so far, the evidence remains elusive, leaving scientists to wonder what other hidden phenomena might be lurking in the galactic core. The galactic center is more than just a scientific curiosity. It's a window into the forces that shape our universe. From the violent interactions around Sagittarius to the potential presence of dark matter, this region challenges our understanding of gravity, matter, and the very fabric of space-time. But as we peer into this cosmic crucible, one question lingers: what lies at the heart of our galaxy? Could it hold clues to the nature of dark matter, the origins of stars, or even the ultimate fate of the universe? As we continue to explore, we're reminded that the galaxy's core is not just a place of mystery, it's a frontier of discovery, waiting to reveal its secrets. Deep within the cosmos, where galaxies swirl in a delicate dance of gravity and light, an extraordinary event unfolded, one that would change our understanding of the universe forever. This is the story of the Bullet Cluster, a cosmic collision so powerful that it not only revealed the hidden architecture of the universe, but also provided some of the strongest evidence for the existence of dark matter. The Bullet Cluster is actually two galaxy clusters, massive collections of galaxies, gas, and dark matter that collided and passed through each other at staggering speeds. This cosmic smash-up occurred hundreds of millions of years ago, but its aftermath is still visible today. What makes this event so remarkable is the way it separates ordinary matter from something far more mysterious. When the clusters collided, their hot gas clouds packed with visible matter slammed into each other and slowed down, creating a shock wave that heated the gas to millions of degrees. Meanwhile, the dark matter in each cluster, which doesn't interact with light or ordinary matter, continued moving through space unaffected by the collision. The result, a striking separation between the glowing gas, visible in X-rays, and the invisible dark matter, mapped through gravitational lensing. It's as if the universe itself drew a map showing us where the dark matter lies. This separation is a game-changer for our understanding of gravity and the cosmos. Before the Bullet Cluster, some scientists proposed alternative theories of gravity, suggesting that dark matter might not exist and that our understanding of gravity itself needed revising. But the Bullet Cluster's clear distinction between visible matter and dark matter dealt a blow to these theories. If gravity worked differently, as these alternatives suggested, we wouldn't see such a stark division between the two. The cluster's behavior aligns perfectly with the idea that dark matter is real and invisible, massive substance that shapes the universe on the largest scales. The implications of this discovery are profound. The Bullet Cluster not only supports the existence of dark matter, but also gives us a rare glimpse into its behavior. It shows us that dark matter doesn't just sit idly in space. It interacts gravitationally, clumping together to form the scaffolding for galaxies and galaxy clusters. Without it, the universe as we know it would look very different. Yet, for all we've learned, dark matter remains elusive. We still don't know what it's made of or how it fits into the broader picture of particle physics. The Bullet Cluster is a crucial piece of the puzzle, but the mystery is far from solved. So, could the Bullet Cluster be the smoking gun for dark matter? Its evidence is compelling, but it also raises new questions. How does dark matter behave on smaller scales? What particles make it up, and how do they interact with the rest of the universe? As we continue to study this cosmic collision and others like it, we're reminded that the universe is full of surprises, each one challenging our assumptions and expanding our understanding. And as we turn our gaze to the next mystery, we're left with a tantalizing thought. What other cosmic secrets might be waiting to be uncovered, hidden in the depths of space? The Bullet Cluster is more than just a snapshot of a violent event. It's a window into the unseen forces shaping our universe. It reminds us that even in the chaos of a collision, there's order, a hidden structure that guides the cosmos. And as we explore further, we're reminded that the universe is always one step ahead, daring us to keep up with its endless mysteries. What other cosmic enigmas might be waiting to reveal themselves, hidden in the vast expanse of space? The journey to find out is just beginning. Now, let's venture into one of the most peculiar and unsettling regions of the cosmos, the Boötes Void. Imagine a vast, dark expanse stretching across an astonishing 330 million light-years, where galaxies are almost entirely absent. This is the Boötes Void, a cosmic desert so empty that it's been dubbed the Great Nothing. To put its scale into perspective, if the Milky Way were placed at the center of this void, our nearest galactic neighbor would be millions of light-years away. It's a place where the usual bustling activity of the universe gives way to an eerie stillness, raising profound questions about the nature of space itself. The discovery of the Boötes Void dates back to the 1980s, when astronomers mapping the distribution of galaxies noticed an unusually sparse region in the constellation of Boötes. Instead of the dense clusters and filaments that characterize much of the universe, this area was strikingly barren, containing only a handful of galaxies. At first, scientists wondered if it was a mistake, a gap in their data, or an artifact of their observations. But further studies confirmed its existence, revealing a region so empty that it defied expectations. How could such a vast expanse of space contain so little matter, and what does its existence mean for our understanding of the cosmos? One leading theory suggests that the Boötes Void might be the result of a cosmic tug-of-war. In the early universe, regions of slightly higher density attracted matter, growing into the galaxies and clusters we see today. Meanwhile, regions of lower density were left behind, eventually becoming voids. The Boötes Void could be an extreme example of this process, a place where matter was so thinly spread that galaxies never had the chance to form. But even this explanation doesn't fully account for its sheer size. Could there be something more at play, perhaps a force or process we haven't yet identified? Another intriguing possibility is that the Boötes Void isn't as empty as it seems. Some theorists propose that it could be filled with dark matter, the invisible substance that makes up most of the universe's mass. If true, this would mean the void isn't truly empty, it's just hiding its contents in a form we can't see. Alternatively, the void might contain faint, diffuse galaxies that are too dim for our current telescopes to detect. These galaxies could be relics of an earlier era, remnants of a time when the universe was younger and less structured. The existence of the Boötes Void also has profound implications for the large-scale structure of the universe. It challenges our understanding of how matter is distributed across the cosmos and raises questions about the role of voids in shaping its evolution. Are voids like the Boötes Void rare anomalies, or are they more common than we realize? Could they play a role in the universe's expansion, influencing the flow of galaxies on the largest scales? The answers could reshape our understanding of the cosmic web, the intricate network of filaments and voids that defines the universe's architecture. So, is the Boötes Void a cosmic anomaly, or is it a sign of something deeper? Its vast emptiness forces us to confront the limits of our knowledge and consider the possibility that the universe still holds secrets we're only beginning to uncover. As we peer into this enigmatic region, we're reminded that the cosmos is full of surprises, each one challenging our assumptions and expanding our horizons. And as we turn our gaze to the next mystery, we're left with a lingering question. What other hidden wonders might be waiting to reveal themselves in the vast expanse of space? In the vast expanse of the cosmos, where stars shine with predictable rhythms, one star stands out as a true enigma, Tabby's star, also known as KSE 8,462,852. This unassuming star, located about 1,400 light-years away in the constellation Cygnus, has baffled astronomers with its bizarre and irregular dimming patterns. Unlike most stars, which dim slightly and predictably when planets pass in front of them, Tabby's star experiences dramatic and erratic dips in brightness, sometimes fading by as much as 22%. These fluctuations are so unusual that they've sparked a flurry of theories, from the mundane to the extraordinary. Could this strange behavior be a sign of something truly unprecedented, like alien megastructures? When the star's peculiar dimming was first discovered by the Kepler Space Telescope in 2015, scientists were quick to propose natural explanations. One leading theory suggests that the star might be surrounded by massive clouds of dust and debris, possibly from a shattered planet or a swarm of comets. As these fragments orbit the star, they could periodically block its light, causing the irregular dimming we observe. Another possibility is that the star itself is undergoing internal changes, such as fluctuations in its brightness or magnetic activity, though these explanations struggle to account for the sheer scale of the observed dimming. While these natural scenarios are plausible, none fully explain the star's behavior, leaving room for more speculative ideas. This is where the notion of alien megastructures comes in. In the 1960s, physicist Freeman Dyson proposed the idea of a Dyson sphere, a hypothetical structure built by an advanced civilization to harness the energy of a star. While a full Dyson sphere would completely encase the star, smaller versions, known as Dyson swarms, could consist of countless orbiting panels or habitats, partially obscuring the star's light. Could Tabby's star be home to such a structure? The idea is as thrilling as it is controversial, capturing the imagination of scientists and the public alike. While the odds of finding alien engineering are undeniably slim, Tabby's star's behavior has made it a prime candidate in the search for extraterrestrial intelligence. Yet, the search for answers is far from over. Observations from ground-based telescopes and space observatories continue to monitor the star, hoping to catch it in the act of dimming and gather more clues. Recent studies have found evidence of fine dust particles around the star, supporting the idea of a natural explanation. However, the irregularity and scale of the dimming still defy easy explanation, keeping the mystery alive. Whether the cause is cosmic debris or something more extraordinary, Tabby's star serves as a reminder of how much we still have to learn about the universe. What makes this star so compelling is not just its strangeness but what it represents. If its dimming is caused by natural phenomena, it could teach us about the chaotic processes that shape planetary systems. If, on the other hand, it's evidence of alien engineering, it would be one of the most profound discoveries in human history. Either way, Tabby's star challenges us to think beyond our current understanding and consider the vast possibilities that lie hidden in the cosmos. So, could Tabby's star be evidence of alien technology? While the answer remains elusive, the question itself invites us to explore the universe with curiosity and wonder. As we turn our gaze to the next cosmic mystery, we're reminded that the stars above hold secrets beyond our wildest imagination, secrets that might one day reveal the true nature of our place in the cosmos. Now, let's shift our focus to a mystery that's literally close to home: the enigmatic solar corona. This shimmering halo of plasma, the Sun's outer atmosphere, is one of the most dazzling and puzzling features of our star. While the Sun's surface, or photosphere, burns at around 5,500 degrees Celsius, the corona soars to temperatures of over 1 million degrees. It's as if the air around a campfire were somehow hotter than the flames themselves, a paradox that has baffled scientists for decades. How can the Sun's outer atmosphere be so much hotter than its surface, and what does this mean for our understanding of solar physics? The mystery deepens when you consider the Sun's structure. Heat typically flows from hotter regions to cooler ones, yet the corona defies this basic principle. The photosphere, the layer we see as the Sun's surface, radiates energy outward, but something extraordinary happens as you move further out. The corona, extending millions of kilometers into space, becomes unimaginably hotter. This phenomenon, known as the coronal heating problem, has puzzled astronomers since the 1940s, when the corona's extreme temperatures were first measured during solar eclipses. What could possibly drive this counterintuitive heating? One leading theory points to the Sun's magnetic field as the key player. The Sun is a swirling cauldron of magnetic activity, with lines of magnetic force constantly twisting, snapping, and reconnecting. These magnetic interactions, known as nanoflares or magnetic reconnection events, could release bursts of energy that heat the corona. Imagine a tangled bundle of rubber bands suddenly snapping. Each release of tension generates a tiny burst of heat. On the Sun, this process could happen millions of times a second, collectively raising the corona's temperature to staggering levels. While this theory is compelling, it's still unclear whether these events alone can account for the corona's immense heat. Another intriguing possibility involves waves of energy traveling through the Sun's plasma. Alfvén waves, named after Swedish physicist Hans Alfvén, are ripples in the Sun's magnetic field that carry energy from the interior to the corona. As these waves travel outward, they could transfer their energy to the corona, heating it in the process. Think of it as shaking a rope. The energy from your hand travels along the rope, creating waves that dissipate as heat. If Alfvén waves are indeed responsible, they could provide a steady flow of energy to keep the corona blazing. Yet, despite decades of research, scientists are still working to confirm this mechanism and understand its full impact. The implications of solving this mystery extend far beyond the Sun itself. The corona is the source of the solar wind, a stream of charged particles that flows through the solar system, influencing space weather. When the Sun's magnetic activity spikes, it can unleash solar flares and coronal mass ejections, sending bursts of energy and particles toward Earth. These events can disrupt satellites, power grids, and even astronaut safety. Understanding how the corona works is crucial for predicting and mitigating these effects, making it not just a scientific curiosity but a matter of practical importance. So, what heats the Sun's corona to such extreme temperatures? Is it the snap and crackle of magnetic fields, the rhythmic dance of Alfvén waves, or something entirely unexpected? As we continue to probe this cosmic enigma, we're reminded that even the star at the center of our solar system still holds secrets waiting to be uncovered. And as we turn our gaze to the next mystery, we're left with a tantalizing question. What other forces might be at work in the heart of our Sun, shaping the very fabric of our solar system? Now, let's turn our attention to the Moon, a celestial neighbor so familiar, yet still full of surprises. Among its craters and plains lies one of the most visually striking and scientifically puzzling features: lunar swirls. These bright, swirling patterns, resembling delicate brushstrokes on a cosmic canvas, stand out starkly against the Moon's dark, dusty surface. Some swirls stretch for hundreds of kilometers, their intricate designs almost appearing as if they were painted by an unseen hand. But what could create such mesmerizing patterns on an otherwise barren world? The answer, it turns out, is as mysterious as the swirls themselves. Lunar swirls have fascinated scientists since they were first observed in detail during the Apollo missions. Unlike the Moon's typical gray terrain, these regions reflect more sunlight, giving them their distinctive brightness. Yet their origin remains a topic of heated debate. One leading theory points to the Moon's magnetic fields. Unlike Earth, the Moon doesn't have a global magnetic field, but it does have localized patches of magnetism. These magnetic anomalies could deflect the solar wind, a stream of charged particles from the Sun, preventing it from darkening the surface. Over time, this shielding effect might leave behind the bright, swirling patterns we see today. It's as if the Moon's magnetic fields are cosmic artists, sculpting light and shadow into breathtaking designs. But magnetic fields aren't the only possible explanation. Another compelling idea involves comet impacts. When a comet strikes the moon, its icy nucleus vaporizes on impact, creating a temporary atmosphere. This atmosphere could interact with the lunar surface in ways that alter its reflectance, leaving behind bright swirls. The impact shockwaves might also redistribute fine dust particles, enhancing the swirl's visibility. While this theory is intriguing, it raises questions. Why do some swirls appear in regions with no evidence of recent impacts? And why do they maintain their brightness over millions of years? These puzzles keep scientists searching for answers. The significance of lunar swirls goes beyond their beauty. They offer a unique window into the moon's history and geology. By studying these patterns, scientists can learn more about the moon's magnetic past, its interactions with the solar wind, and even the nature of impacts from comets and asteroids. Understanding lunar swirls could also shed light on similar features found on other airless bodies, like Mercury or asteroids, helping us piece together the broader story of our solar system's evolution. But for now, these enigmatic patterns remain a tantalizing mystery, inviting us to explore further. What could have created these swirling masterpieces on the moon? Are they the result of ancient magnetic fields, the remnants of cosmic collisions, or something entirely unexpected? As we ponder these questions, we're reminded that even our closest celestial neighbor still holds secrets waiting to be uncovered. And as we prepare to explore the next cosmic enigma, we're left with a sense of wonder, eager to see what other mysteries the universe might reveal. Now, let's turn our gaze to a subtle yet captivating phenomenon that often goes unnoticed: the zodiacal light. On a clear, moonless night, far from the glare of city lights, you might spot a faint, triangular glow rising from the horizon just after sunset or before sunrise. This ethereal light, often described as a soft, hazy pyramid, is the zodiacal light, a celestial mystery that has intrigued astronomers for centuries. But what exactly is this ghostly illumination, and why does it shine brighter than our current understanding of the solar system can explain? The zodiacal light is sunlight scattered by countless tiny dust particles orbiting the sun. These particles, remnants of comets, asteroids, and even collisions between larger bodies, form a vast, flattened cloud that stretches across the plane of the solar system. When sunlight hits these grains, it scatters in all directions, creating the faint glow we see. It's a bit like sunlight catching dust motes in a sunbeam, but on a cosmic scale. Yet, there's a catch. The amount of dust we've detected doesn't seem to account for the zodiacal light's brightness. So, where is all this extra dust coming from? One possible explanation lies in the inner solar system, where a steady rain of debris from comets and asteroids continuously replenishes the dust cloud. As these icy and rocky bodies pass close to the sun, they shed material, leaving behind trails of dust that accumulate over time. However, even this process doesn't fully explain the zodiacal light's intensity. Could there be another source, perhaps a reservoir of dust we haven't yet identified? Some scientists speculate that a population of small, faint asteroids or even interstellar dust might be contributing to the glow, adding to the mystery. The zodiacal light isn't just a beautiful sight, it's also a valuable tool for understanding the solar system's evolution. By studying its properties, astronomers can map the distribution of dust in the inner solar system and learn more about the processes that shape it. For example, variations in the light's brightness and structure could reveal clues about the orbits and compositions of the dust particles, shedding light on the history of comets, asteroids, and other small bodies. It's like using a flashlight to illuminate the hidden corners of our cosmic neighborhood. But the mystery doesn't end there. The zodiacal light's unexpected brightness raises questions about the dynamics of the solar system's dust cloud. Could there be more dust than we've accounted for, or is the dust we see somehow more reflective than we thought? Some researchers have even proposed that the zodiacal light might be influenced by interactions with the solar wind or magnetic fields, adding another layer of complexity to this cosmic puzzle. So, what exactly is the source of the zodiacal light? Is it the result of familiar processes like the disintegration of comets and asteroids, or does it hint at something more exotic? As we continue to explore this enigmatic glow, we're reminded that even the most subtle phenomena can hold profound secrets waiting to be uncovered. And as we turn our gaze to the next cosmic mystery, we're left with a sense of curiosity, eager to see what other hidden wonders the universe might reveal. Now, let's explore a cosmic structure so vast it defies imagination, the Hercules-Corona Borealis Great Wall. This colossal formation, stretching an astonishing 10 billion light-years across, is one of the largest known structures in the universe. To put that into perspective, if the Milky Way were the size of a grain of sand, the Hercules-Corona Borealis Great Wall would span the length of a football field. It's a cosmic megastructure that challenges our understanding of the universe's architecture and raises profound questions about how such an immense formation could exist. The Hercules-Corona Borealis Great Wall was discovered in 2013 by a team of astronomers studying gamma-ray bursts, brief but incredibly energetic explosions of light. These bursts, often associated with the deaths of massive stars, serve as cosmic beacons, illuminating the distant reaches of the universe. By mapping their locations, scientists noticed an unusual concentration of gamma-ray bursts in the constellations of Hercules and Corona Borealis, hinting at the presence of a massive structure. Further analysis revealed a staggering collection of galaxies, galaxy clusters, and dark matter, all bound together by gravity in a vast filamentary wall. What makes this structure so baffling is not just its size but how it fits, or doesn't fit, into our understanding of the universe's large-scale structure. According to the cosmological principle, a cornerstone of modern cosmology, the universe should appear roughly the same in all directions when viewed on a sufficiently large scale. This means that matter should be distributed evenly, without any single structure dominating the cosmic landscape. Yet, the Hercules-Corona Borealis Great Wall seems to defy this principle, presenting a glaring anomaly that challenges our foundational theories. How could such a massive structure form in a universe governed by uniform distribution? One possibility is that it's the result of cosmic inflation, a period of rapid expansion just after the Big Bang. During this time, tiny fluctuations in density could have grown into vast structures over billions of years. Alternatively, the wall might be a product of gravitational interactions, where smaller structures merged over time to form something truly colossal. But even these explanations struggle to account for the sheer scale of the Hercules-Corona Borealis Great Wall, leaving scientists to wonder if there's more to the story. The implications of this discovery are profound. If structures like the Hercules-Corona Borealis Great Wall are more common than we realize, it could mean that our understanding of the universe's large-scale structure is incomplete. Perhaps we're missing a key piece of the puzzle, a force or process that shapes the cosmos in ways we don't yet understand. This structure could be a hint that the universe is far more complex and varied than our current models suggest, pushing us to rethink everything from the Big Bang to the ultimate fate of the cosmos. So, could the Hercules-Corona Borealis Great Wall be a cosmic anomaly, or is it a sign of something deeper? Its discovery reminds us that the universe is full of surprises, each one challenging our assumptions and expanding our horizons. And as we turn our gaze to the next mystery, we're left with a lingering question. What other colossal structures might be lurking in the depths of space, waiting to reshape our understanding of the cosmos? Now, let's dive into one of the most dramatic and fascinating processes in the cosmos, the phenomenon of cannibal galaxies. These cosmic giants don't just grow by forming new stars, they devour their smaller galactic neighbors in a process known as galactic cannibalism. It's a tale of cosmic survival where the strong consume the weak, reshaping the universe one collision at a time. But how exactly does this celestial feast work, and what does it tell us about the life and death of galaxies? Galactic cannibalism occurs when a larger galaxy, often a massive elliptical galaxy, gravitationally pulls in and absorbs a smaller one. Over billions of years, the smaller galaxy is torn apart, its stars, gas, and dark matter assimilated into the larger galaxy's structure. This process isn't just a random act of cosmic violence, it's a key driver of galaxy evolution. By consuming smaller galaxies, larger ones grow in size, mass, and complexity, becoming the behemoths we observe today. The Milky Way itself is no stranger to this process. Evidence suggests it has consumed smaller galaxies in the past, and it's currently in the process of merging with the Large Magellanic Cloud. But here's where the mystery deepens. How do cannibal galaxies maintain their structure after such violent collisions? When two galaxies collide, their stars don't actually crash into each other. Space is too vast for that. Instead, their gravitational fields interact, distorting their shapes and flinging stars into chaotic orbits. Over time, the larger galaxy's gravity dominates, pulling the smaller one apart and assimilating its material. Yet, despite this chaotic process, the larger galaxy often emerges with a relatively stable, smooth structure. This raises intriguing questions about the forces at play during and after these collisions. Is it the dark matter halo that helps stabilize the galaxy, or do the stars and gas eventually settle into a new equilibrium, like water finding its level? One clue lies in the role of dark matter. This invisible substance, which makes up most of a galaxy's mass, forms a vast halo that extends far beyond the visible stars. During a collision, the dark matter halos of the two galaxies interact and merge, creating a gravitational scaffold that helps the larger galaxy retain its shape. Meanwhile, the stars and gas from the smaller galaxy are dispersed and gradually integrated into the larger one, often forming new structures like tidal tails or shells. These features, visible in images of merging galaxies, are like cosmic fingerprints revealing the history of the collision. Galactic cannibalism isn't just a destructive process, it's also a creative one. When galaxies merge, the influx of gas can trigger intense bursts of star formation, lighting up the galaxy with newborn stars. In some cases, the collision can even reignite a dormant supermassive black hole at the galaxy's center, feeding it with fresh material and causing it to emit powerful jets of energy. These events shape not only the galaxy itself, but also its surroundings, influencing the evolution of the entire cosmic neighborhood. So, what happens when galaxies collide and merge? The answer lies in the delicate balance between chaos and order, destruction and creation. These cosmic encounters are more than just spectacular displays of gravity at work. They're the building blocks of the universe's grand structure. As we continue to study cannibal galaxies, we uncover clues about how galaxies grow, evolve, and shape the cosmos around them. And as we turn our gaze to the next mystery, we're reminded that the universe is a place of endless transformation, where even the most violent events can lead to something beautiful. Between the stars, planets, and galaxies lies a vast, invisible sea, the intergalactic medium. This diffuse gas, made up mostly of hydrogen and helium, fills the seemingly empty spaces between galaxies, forming a cosmic web that connects the universe's largest structures. Though it's often overlooked, the intergalactic medium plays a crucial role in the life cycle of galaxies, acting as both a reservoir of raw material and a record of the universe's history. But this seemingly simple gas holds secrets that challenge our understanding of the cosmos, particularly when it comes to its temperature and density. Why is it so hot in some regions and cooler in others? And what can these variations tell us about the universe's evolution? The intergalactic medium isn't uniform, it's a dynamic, ever-changing environment. In some areas, the gas is sparse and cool, while in others, it's heated to millions of degrees by the energy pouring in from nearby galaxies, quasars, or even ancient supernova. This temperature variation is one of the medium's greatest mysteries. How does such a thin gas manage to retain heat over billions of years, especially when it's spread across such vast distances? One theory suggests that shocks from galaxy collisions or the explosive energy of supermassive black holes could be responsible, injecting heat into the medium and creating pockets of scorching gas. But the exact mechanisms remain unclear, leaving scientists to wonder what other forces might be at play. Adding to the intrigue is the medium's role in galaxy formation. The intergalactic medium is the birthplace of galaxies, providing the raw material from which stars and planets eventually form. As gravity pulls gas into denser regions, it cools and collapses, igniting the fires of new stars and galaxies. Yet, this process isn't always straightforward. The medium's complex temperature and density variations can slow down or speed up galaxy formation, shaping the universe's structure in ways we're only beginning to understand. It's a delicate dance where the interplay of gravity, heat, and density determines the fate of entire galaxies. But the intergalactic medium isn't just a passive player, it's also a cosmic time capsule. By studying its properties, scientists can trace the history of the universe from the aftermath of the Big Bang to the present day. For example, the medium's composition reveals clues about the first stars and galaxies, which ionized the gas and left behind a faint imprint that we can still detect. It's like reading the universe's diary, written in the language of gas and light. Yet for all we've learned, the medium's full story remains incomplete. What other secrets does it hold, and how might they reshape our understanding of the cosmos? As we peer into the depths of the intergalactic medium, we're reminded that even the spaces between galaxies are teeming with activity and mystery. This invisible network of gas is more than just filler. It's a vital part of the universe's fabric, shaping its past, present, and future. And as we turn our gaze to the next cosmic enigma, we're left with a sense of awe, a reminder that the universe is full of surprises, each one waiting to reveal its secrets. What other hidden forces might be at work, quietly shaping the cosmos in ways we've yet to imagine? Now, let's journey back in time to one of the most pivotal moments in the universe's history, the cosmic dawn. This is the era when the first stars and galaxies ignited, illuminating the cosmos after hundreds of millions of years of darkness. Imagine a universe that was once a vast, featureless void, filled only with the faint afterglow of the Big Bang. Then, like a match struck in the darkness, the first stars burst into life, their light piercing the cosmic shadows and setting the stage for everything we see today. But how did this transformation happen, and why does it remain one of the most elusive chapters in the story of the universe? Observing the cosmic dawn is no easy task. This epoch, which began around 100 million years after the Big Bang and lasted for several hundred million years, lies at the very edge of what our telescopes can detect. The light from this era has traveled for over 13 billion years to reach us, stretched and dimmed by the expansion of the universe into the infrared part of the spectrum. To study it, astronomers rely on some of the most advanced instruments ever built, like the James Webb Space Telescope, which peers deep into the early universe to capture the faintest glimmers of starlight. Yet, even with these tools, the cosmic dawn remains shrouded in mystery, its details tantalizingly out of reach. One of the greatest puzzles of this era is how the first stars and galaxies formed in the first place. After the Big Bang, the universe was a hot, dense soup of particles, but as it expanded and cooled, matter began to clump together under the pull of gravity. These clumps grew denser and denser, eventually collapsing to form the first stars, massive, blazing giants unlike anything we see today. These stars, known as population Roman III stars, were made almost entirely of hydrogen and helium, the simplest elements in the universe. Their intense radiation ionized the surrounding gas, carving out the first galaxies and lighting up the cosmos. But how did this process begin, and what triggered the collapse of those first gas clouds? The answer may lie in the interplay between dark matter and ordinary matter. Dark matter, the invisible scaffold of the universe, likely played a crucial role in the formation of the first structures. Its gravitational pull would have drawn ordinary matter into dense regions, creating the seeds for star formation. Yet, the exact mechanisms remain unclear. Did the first stars form in isolation, or were they born in clusters? How did their light spread through the universe, and how did it influence the formation of later generations of stars and galaxies? These questions are at the heart of our quest to understand the cosmic dawn. The implications of this era are profound. The cosmic dawn didn't just light up the universe, it set the stage for everything that followed. The first stars forged heavier elements in their cores, seeding the cosmos with the building blocks of planets, life, and everything we see around us today. Their light also reionized the universe, stripping electrons from atoms and transforming the intergalactic medium into the transparent state we observe today. Without the cosmic dawn, the universe as we know it simply wouldn't exist. But what triggered this transformative era? Was it the collapse of the first dark matter halos, the ignition of the first stars, or something else entirely? As we peer into the distant past, we're reminded that the universe is a place of endless wonder, where even the faintest glimmers of light can illuminate the grandest mysteries. And as we prepare to explore the next chapter in this cosmic story, we're left with a question that lingers in the depths of space and time. What other secrets might the cosmic dawn hold, waiting to reshape our understanding of the universe? Now, let's venture into one of the most mind-expanding ideas in modern science, the multiverse. Imagine a reality where our universe isn't the only one, but just one of countless others, each with its own unique laws of physics, stars, and even life. This isn't science fiction. It's a serious scientific hypothesis that has grown out of some of the most profound discoveries in cosmology and quantum mechanics. But what exactly is the multiverse, and could it truly exist? The concept of the multiverse arises from two major pillars of modern physics: cosmic inflation and quantum mechanics. Cosmic inflation, the theory that the universe underwent a rapid expansion just moments after the Big Bang, suggests that our observable universe might be just a tiny bubble in a much larger, perhaps infinite, cosmic ocean. If inflation happened once, it could have happened countless times, creating an endless array of universes, each with its own distinct properties. Picture a cosmic foam, where each bubble represents a separate universe, expanding and evolving independently of the others. Quantum mechanics, the science of the very small, adds another layer to this idea. According to the many worlds interpretation of quantum theory, every time a quantum event occurs, like the decay of an atom or the spin of an electron, the universe splits into multiple branches, each representing a different outcome. In this view, every possible version of reality exists simultaneously, creating an infinite tapestry of parallel universes. It's a dizzying thought. Every choice you've ever made, every path you didn't take, might have played out in another universe. But how do we know if the multiverse is real? The challenge lies in its very nature. If other universes exist beyond our own, they might be forever hidden from us, separated by vast stretches of space or even different dimensions. Yet, there are tantalizing hints. For example, the cosmic microwave background. The faint afterglow of the Big Bang contains subtle anomalies that some scientists believe could be the fingerprints of collisions between our universe and others. These cosmic bruises might be the closest we'll ever get to direct evidence of a multiverse. The implications of the multiverse are staggering. If true, it would mean that our universe is just one of an infinite number, each with its own unique set of physical laws. Some might be barren, devoid of life or even stars, while others could be teeming with civilizations far more advanced than our own. This idea challenges not only our understanding of the cosmos, but also our place within it. Are we just one possibility among countless others, or is our universe somehow special? And what does it mean for the nature of reality itself? So, could we ever prove the existence of other universes? For now, the answer remains uncertain. The multiverse is a hypothesis that pushes the boundaries of science, blending the observable with the speculative. Yet, it's a testament to human curiosity, a reminder that the universe, or perhaps universes, are full of mysteries waiting to be explored. As we ponder this cosmic puzzle, we're left with a profound question. What other realities might exist just beyond the edge of our understanding, and what could they reveal about the true nature of existence? As we reach the end of our journey through the cosmos, it's worth pausing to reflect on the incredible mysteries we've explored. From the enigmatic dark matter that binds galaxies together to the violent, unseen forces of gamma-ray bursts, the universe continually challenges our understanding and pushes the boundaries of what we thought possible. We've marveled at the bizarre behavior of rogue planets drifting through the void, pondered the origins of the cosmic web, and even dared to imagine the existence of parallel universes. Each of these celestial objects and phenomena tells a story of creation, destruction, and the endless dance of forces that shape the cosmos. These mysteries aren't just scientific curiosities, they're windows into the very fabric of reality. They remind us that the universe is far stranger and more complex than we ever imagined, and that there's still so much we don't know. Take the Hubble tension, for example, a discrepancy in the expansion rate of the universe that could rewrite the rules of cosmology. Or consider the Fermi bubbles, colossal structures that hint at a violent past for our own galaxy. These aren't just puzzles for astronomers, they're invitations for all of us to wonder, to question, and to dream. What makes these mysteries so compelling is their ability to inspire. They remind us that science isn't just about answers, it's about the journey of discovery. Every observation, every theory, and every experiment brings us one step closer to understanding the universe, but it also opens the door to new questions. And that's the beauty of it. The universe is infinite, not just in size, but in the possibilities it holds. Whether it's the search for alien technology around Tabby's star or the quest to understand the extreme heat of the sun's corona, each mystery challenges us to think bigger and dig deeper. As we wrap up, let's remember that these cosmic enigmas aren't just for scientists, they're for all of us. They remind us of our shared curiosity and our place in the grand tapestry of the universe. And while we may not have all the answers yet, that's what makes the journey so exciting. The universe is full of mysteries, and each discovery brings us closer to unlocking its secrets. So, what do you think? Which of these cosmic puzzles fascinates you the most? Share your thoughts in the comments below, and don't forget to subscribe for more explorations into the wonders of space. Together, let's keep looking up and asking the big questions, because the universe has so much more to reveal.